So we're very pleased today to have Wang come and give us a talk on illuminating the nature of cosmic acceleration. I know Yun very well. We work on Euclid together. We both leads of the Galaxy Clustering Science Working Group. So we've worked together for, I'm just going to say many, many years. Also has interests in Roman Space Telescope and is PI for a number of proposed NASA space missions, including Ischia, which she will now pronounce properly, and Atlas. She's a senior research scientist IPAC at Caltech. So take it away, Yun.
Thank you, Will. It's my pleasure to share my thoughts on cosmic acceleration or dark energy, as its unknown reason has been called, with you today. Let's see. Wait, why can't I go to the next slide? Okay, right. So first I'll remind you why we care about solving the mystery of cosmic acceleration. Then I'll talk briefly about Euclid. I'm sure you've heard a lot from Will about that. Then I will talk a little more about the Roman Space Telescope, and then finally Atlas Explorer. I will actually not talk about Ischia today, but you're welcome to ask me about it. Okay, so this is ancient history for some of you, probably before you were born, right? So this is 1998, when the existence of dark energy was first observationally discovered. So in the left panel, you can see the data color-coded red and green from two fiercely competitive and independent teams of observers. So honestly, it's hard to see what's going on, which is why I immediately, took their data and compared and found actually for some of the supernovae that both they actually did not give quite the same numbers. So anyway, so I cleaned up the data and did flux averaging, which I've shown minimizes the systematic effect due to the wavelengths of supernovae. Then I get this beautiful plot that does show that the data as of 1998 seem to favor a flat universe dominated by a cosmological constant. So why do we say this is cosmic acceleration? Again, aiming for the students amongst you who don't know this in your sleep, right? So in the bottom box, you can see this is because the deceleration parameter is given by omega matter divided by 2 minus omega lambda. So if there's only matter in the universe and nothing weird like cosmological constant, as astronomers thought for many, many decades, and they were actually trying to measure the deceleration parameter, right? Because when you only have omega matter, this Q0 deceleration parameter is positive. But the shock in 1998 was that they measured Q0 and it's negative, which means that contrary to our expectations, the universe was actually speeding up its expansion, not decelerating. So, okay, what a shame. We still don't know why. Could be dark energy, catching phrase. So where did that come from? Well, so the equation of state, right? Pressure over density. Matter, well, in cosmology, we take it to be pressureless. And radiation, that well, right? Rho over 3. And cosmological constant, which fits that data beautifully, gives an equation of state of -1, right? So that makes us think, well, whatever this is, we can explain it by introducing something called dark energy with equation of state W subscript X, which could be a function of redshift, right? So calling it dark energy is really parameterizing our ignorance. And also, it's kind of a poetic phrase. I'm saying that as a poet, so I really know. I even wrote a poem titled Dark Energy. So here is cosmology on one slide for the students amongst you. And I'm sure the professors will look up on this fondly, right? So this is all the stuff that we know and love. So the background geometry of our universe is described by the Robertson-Walker metric, a maximally symmetric, simplest possible metric that describes a three-dimensional expanding universe. Okay, so where little a as a function of t is a cosmic scale factor that increases with time because the universe is expanding. Then, of course, Einstein's equation tells us how geometry of the universe, left-hand side here, is related to what's in the universe on the right-hand side, right? Matter, radiation, dark energy, whatnot, okay? And then, of course, what most of us use most frequently is the Friedmann equation on the bottom here that gives the Hubble parameter or expansion rate of the universe as a function of redshift or time, right? And shows how it depends on what the universe is made of, right? Matter, radiation, dark energy, you know, noted with X here, right? And K is the curvature constant. Okay, so what could dark energy be? Well, this is a really old slide. I have not bothered updating it because there has been no, you know, revolutionary advance that I feel compelled to add to this. You get a pretty good sense of what's out there. There's the cosmological constant, which Einstein introduced in 1917 to make sure that the universe doesn't collapse upon itself, right? To hold the universe up, so to speak. And then when he found out that Hubble discovered that the universe is actually expanding and did not need his help, then, you know, he did not push that forward. So some people like to call that Einstein's biggest blunder. So anyway, that's sensational, but most likely not true. So in any case, however, very shocking that cosmological constant has come back, you know, in a huge way, because right now it's actually the simplest possible model for dark energy that fits just about everything. Then the second category is actually a huge subfield in its own, quintessence. Really, here I use it to refer to all the scalar field models out there that try to explain dark energy. So I did my PhD working on models for inflation, right? So I know how it works, right? So for theoretical particle physicists, when we don't know something, you know, just introduce a new scalar field and try to call it phenomenological, and then try to link it to some possibly vague, extremely early physics. Well, again, right, parameterizing our ignorance. Then the next category, much less worked on, quiescence, is more exotic because it actually modifies the kinetic term. So I won't go into detail there. You can look it up if you're interested. Then finally, it's a huge subfield of modified gravity, where I've given you some flavors here. And just by reading the names here, you get a sense that this is a pretty fun and happening field, right? There's vacuum, metamorphosis, or modified Friedmann equation, or phantom dark energy from quantum effects, or back reaction of cosmological perturbations, or emergent gravity. Okay, so now, how do we know which of those is true? Before we talk about how we can observationally determine that, let's discuss a couple of perhaps more subtle points. First is that I've always argued, instead of talking about measuring the equation of state of dark energy, you should actually measure the density of dark energy. Well, say, what's the big deal? Well, in the Friedmann equation, you see the dark energy density is on the same footing as matter density, so it's more fundamental. What's a bigger point is that in particle physics models for dark energy density may not even be positive definite. Okay, so if you're always going after, if you only if you're singularly focused on dark energy equation of state, then you say you had integrated to get dark energy density, then it's always positive definite. Then you may miss out some subtlety in dark energy density, may come to the wrong conclusion. Okay, so what we really want to know is, well, what is this dark energy density as a function of time? Does it change with time? The other fine point is that when we talk about testing gravity, what do we mean? Well, it's really measuring metric. So I showed you the background Robertson-Walker metric, right? So that's the background metric without anything in the universe that none of us would want to live in. So here, now I show you the perturbed Robertson-Walker metric with stuff in it. You know, that's the universe we live in, but in different gauge, so it looks a little bit different, you know. So this is the conformal Newtonian gauge, for those of you who care. So this little a is still the cosmic scale factor, tau's conformal time. So here, you see there's more symmetry, okay, between the time dimension and the space dimensions, okay? So this little phi is the gravitational potential in the Newtonian limit that we know and love. We're extremely familiar with that, okay? And now there's another potential, psi, okay? In general relativity, that's Einstein's theory for gravity, it's equal to phi, okay? However, if gravity is modified, or if general relativity needs to be modified, they need not be equal, okay? So now, right away, you know, we need to measure phi and psi both, okay? So this is why we need both weak length and galaxy clustering measurements. Why? I show you down here. So weak length and the sum of phi and psi, because weak length, as you all know, measures how the images of galaxies are distorted by the distribution of matter in the universe, okay? And so depends on propagation of light. And light rays follow geodesics. That's setting the ds equal to 0 in a metric above there. Right away, you see that give you phi plus psi. While galaxy clustering, in which we can measure phi, the Newtonian potential, using redshift space distortions. I'm sure you've heard a lot about that from Will, right? So where we use peculiar velocities, which follow the gradients of the Newtonian potential. Okay, so now you see, you really need both galaxy clustering and weak lensing to break the degeneracy and measure both of these potentials so we can actually test gravity. Okay, so naturally, next, how do we probe dark energy? Well, the simplest way to think about this is that you need to measure two histories of the universe. One, obviously, is the expansion history of the universe, or equivalently, the dark energy density as a function of redshift or time, okay? So that tells us if dark energy is a cosmological constant. And second function we need to measure is the growth history of cosmic large-scale structure, by which we mean measuring either the growth rate, which we call F, I add a little G there to differentiate from other Fs out there, right? Or the growth factor, capital G, okay, they're related. So this tells us if gravity, AKA general relativity, is modified, given the same expansion history of the universe. So here are the 4 methods for probing dark energy that have been most explored by people. Okay, so the first method is to use type 1a supernovae as cosmological standard candles. I should say calibrate that as standard type 1 supernovae as cosmological candles that can be calibrated to be nearly standard. You get the picture there, right? They're systematics. So this is how we know there is dark energy in the universe. So this method is independent of the clustering of matter and probes expansion history of the universe. An interesting, more recent development is that we've shown that actually you can measure the weak lensing of type 1A supernovae and use that information to probe the clustering of matter. So we can actually get more of the supernovae than what people thought previously. Second method, my favorite method, is to use the 3D distribution of galaxies, which we call galaxy clustering, including baryon acoustic oscillations as standard ruler and redshift space distortions to probe the growth rate. Okay, and the BAO is calibrated by the cosmic microwave background, as you all know, right? Probes the Hubble parameter directly. And I won't, hash all those because I'm sure you're all very familiar with all of that from what Will have shared with you guys. And then also weak lensing can be used to probe dark energy different ways. And you can do cross correlation cosmography. Here though, you are always probing a combination of the growth factor and the expansion rate of the universe. You can't actually separate them. So again, you see here's another way. Galaxy clustering and weak lensing are perfectly complementary to each other. And finally, many people working on using the statistics of galaxy clusters to probe dark energy. That also probes a combination of the Hubble parameter and the growth factor. It's actually related to weak lensing. Okay, so here's a really old slide that can illustrate how using these two measurements or the measurement of these two functions, you can hope to advance the understanding of cosmic acceleration. Okay, so the top plot shows that if you measure the expansion history of the universe, right, and you can tell if it's dark energy is constant or not. So the green line you may not be able to see is lambda CDM with omega matter 0.3. Okay, and the solid line is a kind of weird expansion history of the universe that comes from DGP gravity that was in vogue in 2008, not anymore. I think it's more or less ruled out already. So anyway, just trying to make a point here. So now you see, if you only have expansion history of the universe, you won't know if the expansion history of the universe you are measuring comes from something like a cosmological constant, but with weird, scalar field, so has a strange potential that explains the expansion history of the universe, or if it actually comes from modified gravity, okay? But if gravity is modified, then the growth of large-scale structure in the universe would be different from what we expect in general relativity. So in the bottom plot, you see then you break the degeneracy of these two models that have the same identical expansion history of the universe, but one is dark energy, that's the dashed line there, and solid line is DGP gravity. Okay, you can actually tell them apart. It's pretty amazing. That's why I love galaxy clustering. Okay, and as promised, right, I want to remind you guys why we still care about solving the dark energy problem. It really goes down to a very human level, okay? It's our primordial curiosity, because what dark energy is, or what is causing the observed cosmic acceleration, will determine the ultimate fate of the universe. As you can see in this physical review letter cover plot that Max Tegmarker and I made, well, so long ago. Depending on what dark energy is or is not, okay, the universe may coast along forever, until everything dies, proton decays, there will be nothing left. Or the universe may end up in big rip or big crunch. So in this plot, right, we're plotting the density of dark energy as a function of redshift. So the future is on the left, while the past is on the right. So now the frustrating thing is that we have, well, including me and the junior people I've supervised over the last couple of decades, right? We have measured dark energy density as a function of redshift, as you can see an example of in the bottom left panel here. Okay, I have many different versions of this plot. Okay, so the frustrating thing is that the deviations from a cosmological constant have come and gone over the last 2 decades. Okay, so that's really telling us that we do not have the definitive data set that can illuminate the nature of cosmic acceleration, that there are significant unknown systematics in the methods we use to probe cosmic acceleration. And so that's what's behind this plot, right, this slide here. Okay, so now, of course, we have lots of exciting future projects coming, and DESI is already happening. Okay, very exciting. And Rubin Observatory, Euclid, and the Roman Space Telescope will also, come within the next decade. And all of these will significantly advance our understanding of the nature of cosmic acceleration. However, what I will argue is that we need something even beyond any of those. Okay. Oh, by the way, so here's a beautiful plot that I made with the help of a graphics artist to remind you again why we say it's cosmic acceleration. Okay, it's plotting the time derivative of cosmic scale factor as a function of age of the universe in billion years. Okay, so on the left you can see cosmic deceleration due to matter. Okay, which will keep on going forever if there's no dark energy. So there's cosmic acceleration because that curve actually bends over. It's the cosmic acceleration that have been discovered in 1998. Okay, it's due to dark energy or whatever it is behind cosmic acceleration. So now going on to what's coming in the future, there's Euclid, and I will actually just flash this. Okay, so it was selected in 2011 by ESA. Well, you know all this already, but here's a beautiful picture of Euclid. And so what's new here is the launch vehicle now is changed to TBD, to be determined, but will probably be SpaceX, and Euclid will be launch ready in 2023. You might say, why the change in launch vehicle? You probably would have guessed, right? It's because of the war in Ukraine. So Euclid is already built and integrated, as you see in the left figure here. Okay, and it's going through launch readiness tests. And so the right figure shows you that the instruments we'll use to probe dark energy are on there. Excuse me. Right, so there's the visible instrument that's covered in black here. And then there's a near infrared spectroscopy and photometry instrument that covered in gold here. So Euclid will carry it out as its core survey, an extremely wide survey over nearly 15,000 square degrees. And so that's the area indicated bound by the blue contours, okay? The galactic center, obviously. And so we hope to get approximately 30 million H-alpha emission line galaxies at line flux of 2 × 10⁻16 ergs per second per centimeter squared, and over redshift 0.9 to 1.8. And again, I'm sure you are already familiar with that. So as Will said, he and I work very closely, well, well over a decade now. So yeah, so we have this very active galaxy clustering science working group in Euclid, working on all the things we need to do to get ready to use the spectroscopic survey over nearly 15,000 square degrees from Euclid to probe cosmic acceleration. Okay, again, I just want to flash this mainly to tell you that I work at Euclid NASA Science Center, which we call NSCI, at IPAC at Caltech. And so we do have a website with lots of useful tools. Will be released by both ESA and our website. And since you guys are located in North America, you may find this of interest. Sorry. So going on to the next big thing in space mission for dark energy, there's W first. Long story there, so I actually got involved along that line of inquiry in 2004 when I came up with a mission concept for the joint dark energy mission, which I called JEDI. Isn't that the best acronym ever? So anyway, and so there were several mission concepts for JDAM, and well, eventually for various reasons, NASA canceled JDAM. However, in a 2010 astrophysics decadal survey, the decadal committee came up with W first. That's kind of like a combination of something like JDAM plus a couple of other things. Okay, and they ranked it as the top priority for NASA to implement. And NASA did implement. And also, W first was renamed Nancy Grace Roman Space Telescope a couple of years ago, okay, to honor Nancy Grace Roman, a pioneer and scientific leader at NASA. This is a very busy slide. I don't expect you to read it all. I just want to flash this timeline for Roman Space Telescope. So I've been involved from the beginning. I've actually been on all of the committees under different names, called Science Coordination Group or Formulation Science Working Group, whatever. I was on it. I think I only skipped the 6-month interim one because, just didn't seem to be worth my while. Yeah, so now NASA has been very enthusiastic in pushing Roman Space Telescope forward. Phase A started in 2016. I defined the various phases for space mission on top for you here. Okay, so now we are in phase C. Okay, so design development. And phase D, that's the final phase before launch and operations, is expected to start next year. Okay, and the launch is expected for 2027 and could happen as early as 2025. So stay tuned, okay? So it's very exciting. And so what's of interest is that NASA will release a call for proposals for the future science teams under the name of implementation science teams or infrastructure teams in open competition. And the draft announcement already came out last year. And the final formal call should come out any minute now. I think it's held back by some decadal committee related review report, okay? So everyone should be very excited Roman Space Telescope because it's a 2.4 meter space telescope, okay? So wrap your mind around that. So it's the same aperture as Hubble, okay? But in L2, okay? And so what some people have been taken back by is the fact that there are reference surveys for Roman, okay, in dark energy that may not be to people's liking, okay? So I spell it out here, right? So in the notional reference survey, 1.5 years is allocated to wake lensing, while only 6 months is allocated to galaxy clustering, okay? So that's a weird imbalance, okay? So, however, this is notional, okay? So the actual surveys Roman will carry out will be determined in a future open community process organized and chartered by NASA. So stay tuned on that. Finally, you should be very excited to see, if you don't know already, that all Roman data will be made available to the community with no proprietary period. Okay, so everyone can jump on the data right away. Doesn't matter where you are, who you are. And so I should add that in the various Roman top committees I sat on, actually there were a lot of debate about pros and cons with that, you know. So at the end of the day, you know, that's what NASA went with. So here's a schematic of the Roman Space Telescope. And I think it may be boring, you know, for me to point out all different parts. So let's just point to the instrument of interest to this talk, the wide field instrument right here. Can you guys see my arrow, the cursor?
And we? Yeah, yeah, we're
Oh.
small, but yes, we can.
Oh, okay, all right, right here. Oh, all right. All right, so the wide field instrument. What's the big deal there? Well, it can do both imaging and spectroscopy, and also monitor supernovae, okay? And has near-infrared band passes for imaging, spanning 0.48 to 2 microns, huge range, okay? And has a field of view of 0.28 square degrees. So it's 100 times bigger than Hubble, okay, and JWST. Okay, so it's like same aperture as Hubble, but 100 times bigger field of view. That's why it's so powerful. And also has 18 H4RG detectors. Okay, so these are amazing. Okay, so for reference, what Euclid has is H2RG. Okay, so that's, you know, 2K by 2K number of pixels. Okay, so H4RG is the next generation. That's 4K by 4K pixels, huge number of pixels per detector. That's why Roman can have this tiny pixel size of 0.11 arcsecond in the infrared. Okay, pretty spectacular. Okay, so here, more details to get you excited. So Roman will do imaging in R, Z, Y, J, H, H/K, okay, so the wavelength ranges are given here, okay, and the newest development is that Roman will even have imaging in K short, okay, so that was added really to boost general astrophysics. So it's a strong demand, from the astrophysics community, and I'm strongly in favor of that because there was slot for that. Okay, so the K short one, so it's pretty exciting. And also has a very wide filter for 0.93 to 2 for microlensing, since I have that on there. And finally, the GRISM will cover 1 to 1.93 microns. So here I show you the notional wide area survey for Roman. That's at high galactic latitude, of course. So the zodiacal background is lower. Okay, so notionally it covers 2,000 square degrees in both imaging and spectroscopy. And we expect to get around 10 million H-alpha emission line galaxies down to a line flux of 10 to minus 16 ergs per second per centimeter square. However, it's at 6.5 sigma. Well, I'll come back to that again later. And then we expect to get around 2 million oxygen-3 emission line galaxies from redshift 2 to 3. And see what's in yellow here. Okay, we require the redshifts to be measured from spectra with at least 2 emission lines. More about that later. So here you see a beautiful plot that the artists at NASA made based on the Roman galaxy mark that my former postdoc Zhongxu Zai, that some of you know. I still have his previous affiliation with you guys there. Okay, me and Andrew Benson made. Okay, that shows the huge range of cosmic history that the emission line galaxies from Roman will probe. And so on the left here, I call out the emission lines that we will measure to determine redshift. Okay, so for redshift 1 to 2, that's the primary Roman galaxy sample. We will detect and measure both H-alpha and O3 lines. Okay, so we have pretty secure redshifts. And for redshift 2 to 3, we'll have O3 and O2 lines. And so it's all, so in my mind, okay, so it's all about the control of systematics. And since we will be measuring redshifts using a GRISM, right? It's a sleepless spectroscopy. So this is really necessary. More about that later. Sorry. Yeah, so here you can see the forecast from our summary paper on the Roman galaxy clustering science that I led. And so the black data points are the forecasts of what we can get from Roman. So keep in mind, this is the notional 6-month galaxy survey from Roman, okay? It's already pretty spectacular. And in the same paper, we also investigated several other possibilities. So for example, we can have a 10-month much wider survey, okay, that will shrink the error bars by a factor of 2. Or we can have an 18-month survey, which will actually shrink the error bars by a factor of a few. Okay, so that's the one we say would be optimal should the community decide to go with that. Okay, so again, I don't expect you to actually read this, and I won't read it either. And so our paper summarized all the work that we did on the Roman galaxy redshift survey. It's a lot, okay, ranging from pixel level GRISM simulations to the scheduling, okay, of the high latitude spectroscopic survey, I mean the actual implementation, okay, to studies of systematics and so on. Of course, there's a lot more that need to be done. So I want to flash this. It's a slide from David Weinberg that I have modified. Okay, so the message I want to get across is that per unit observing time, Roman, right, being a 2.4 meter space with spectacular near-infrared detectors will be the most powerful facility for probing the nature of cosmic acceleration that's planned and being built and will happen. And so, of course, Roman can do a lot more. How much more time do I have? I should probably speed up, right?
There's no sign of our pizza yet, but maybe 10 more minutes.
Oh, yeah, so definitely speed up so we can get to even more exciting stuff. Okay, so I do want to pause at this Euclid versus Roman comparison. Well, you guys know I love both, right? So I'm very involved with both and plan to continue to do so. And so Euclid and Roman are perfectly complementary to each other. So essentially, Euclid goes shallow and wide, very wide, okay? So Roman goes much deeper, but covers less area. And also Roman can be optimized depending on what Euclid will discover, okay? So while the survey strategy for Euclid is set, right? Because, we'll be launch ready next year. For Roman, we are years behind. Yeah, so we need both, and everyone should be excited about both and try to work on both and use the data from both. So now I alluded to the problem with slitless spectroscopy, which both Euclid and Roman employ. Why? Well, because it's the cheapest way to do spectroscopy. What's the downside? Well, it's pretty messy, okay? So here on the left, you see the image, right? Well, we say direct image because it's not dispersed. On the right, it's what the spectra look like, through the Grism spectroscopy. Okay, so it's pretty, so you can already tell that it's a problem of high sky background because you don't have slits, right? And the overlap. So in astronomy, observers usually do slit spectroscopy that minimizes sky background. Okay, so you can already see where this is going. What's next beyond Euclid and Roman? Slit spectroscopy from space, okay? All taking SDSS, which is at a low redshift, to the high redshift, okay? So Gigi Guzel actually made this plot and I modified somewhat, okay? So here, Gigi showed that Viper's survey, which covers a smallish area, but goes pretty deep, gives you a flavor of the kind of intricate galaxy clustering you see at higher redshift. Okay, so Atlas can take that, can go from redshift 0.5 to 4 over, say, 2000 or 1000 square degrees, okay, with that kind of detail in large scale structure. So I hope you're already excited. So some of you may have heard Atlas as a probe before. So you can ask me about why it's an explorer now, but for now, I'll just focus on what it is now. Okay, so it's a 1 meter aperture space telescope with 0.8 square degree field of view to do R1000 slit spectroscopy over 1 to 4 microns. Okay, and we expect to get 12,000 spectra simultaneously, and all these are slit spectra. and could be launch ready in 2032. And the cost should be within NASA's MIDEX envelope. I have more details on that later. And so Atlas Explorer has 4 science goals. I highlighted the one relevant to this talk in yellow. Trace large-scale structure densely to illuminate the nature of dark energy. So here's the comparison. Why do we need Atlas? First, goes 1, covers 1 to 4 microns, right, beyond Roman and Euclid. Also has significantly higher spectral resolution than either Roman or Euclid, has larger field of view, I should say comparable, okay? And goes much deeper in emission line flux, and we'll get a lot more galaxies, order of magnitude increase from Roman and Euclid. So Atlas Explorer fills a gap in the capability of current and plants in large area, high source density, slit spectroscopy. Okay, so the science driver for Atlas Explorer is actually galaxy evolution. Okay, so I won't bore this audience with all this stuff. So essentially, by doing slit spectroscopy over 1 to 4 microns, we get all of these emission lines that you see in the bottom right figure here. Okay, so galaxy evolution, people are so excited about this, okay? Because then they can actually decode the physics of galaxy evolution. And so Atlas will do two-tiered survey. Okay, the white survey that I told you about, that's one cosmology we'll use. We'll go down to H alpha line flux of 1.4 times 10 to minus 17 ergs per second per centimeter square. Okay, order of magnitude deeper, factor of 10 deeper than Roman. And we expect to get 144 million galaxies with secure redshifts, okay? We'll also do a medium survey that goes much deeper, but only cover 50 square degrees. And even so, that will get us almost 8 million galaxy spectra. Okay, so now the reason that Atlas goes so deep and gets so many galaxy spectra is because galaxy evolution people have told me, their dream is when they close their eyes at night and start dreaming, they want to see the cosmic web. So here in ghostly green is the cosmic web. And so Roman does not really reveal the cosmic web, okay? I give you a hint of that. But Atlas medium survey will in fact trace the cosmic web. And you can only do that with slit spectroscopy. Okay, so here is a comparison. Okay, so on the right, you have photometric surveys. And this is like the best possible photometric redshift you can get, right? 1% redshift accuracy. And you do not see the cosmic web at all. And for Euclid and Roman, you have 0.1% redshift accuracy. You have a fuzzy picture of the cosmic web. Okay, but with a slit spectroscopy, you can get 10 to minus 4 precision in redshift measurement. Here, you actually do see the cosmic web. Okay, so of course, you can do a lot with galaxy evolution. But for cosmology, right, we have all those galaxies. And you may say, well, how do you know how deep to go for the Atlas Wide Survey? Well, because we have this plot from the Atlas 2019 paper that I led. What Atlas will do is essentially getting the redshifts of most of the emission line galaxies in the Roman wavelength ensemble, which has a 10 sigma depth of H of 24 0.7. Okay, so this plot shows the distribution of those galaxies. You see, right, that the peak is at 2 × 10⁻⁻17. Okay, I should say that Atlas probe had a wide survey depth of 5 × 10⁻⁻18, which would actually, go into the tail of this, but we have to disco to Explorer, but still, we are covering beyond the peak. So we expect to get a percent of, or 80% of all of the galaxies in the Roman weak lens ensemble that are emission line galaxies. Okay, so here is the prize, okay, that we are going after. So again, you remember I said we need to measure 2 functions, right? Hubble parameter on the left and growth rate on the right. Okay, so here I'm plotting various other existing or ongoing or future already funded projects, okay, using their official numbers from each, okay? So you see that the Atlas wide survey 3-point statistics will blow everything else out of the water. You may say, well, why can't the other surveys do 3-point statistics? Well, because 2-point statistics, short noise goes as 1/, galaxy number density, okay? While the 3-point statistics has short noise that goes 1/, galaxy number density squared. So you gain huge when you have a very high galaxy number density survey as Atlas wide. And so I argue that Atlas Explorer is what we need to arrive at definitive measurements for cosmic acceleration, right? Because you see we can get 0.5% to 1% precision on H of Z and 1% to a few percent precision in the growth rate. I don't think anything else can beat that. Of course, Atlas does a lot more, right? So can also pierce through galactic plane obscured by dust because it goes to 4 microns. Can even get us Kuiper belt objects. So just a minute on the technology. You might say, well, that sounds great, but how do you do it? Well, the technology driver is the digital micromirror device shown in this picture here from Texas Instrument. That may sound really scary and mysterious. It's actually something you know well, okay? It's what's used in overhead projectors. Hopefully now you say, aha, right? So these things are basically indestructible. They're, so Texas Instrument invested over $1 billion developing those. Okay, so we can use them. And these digital micromirror devices, aka DMDs, have been used in ground-based multi-object spectroscopy for well over a decade. So they really work. So on the left here, this giant column that looks really scary, guess what it is? It's a single human hair, okay? Against the background of this tiny little micromirrors. So each micromirror device consists of 2,000 by 1,000 array of tiny little micromirrors, okay? So each micromirror can tilt only 2 ways or in 2 directions. One can be on, the other can be off. When it's on, the light is sent to the spectrograph or imager, okay? And when it's off, the light is sent to a light dump, okay? Or if you want to do it the best possible way, you can actually, when it's on, you can send the light to a spectrograph. When it's off, you can send the light to an imager. So you're getting imaging at the same time. And so the figure on the right here shows you a preliminary design for Atlas instrument. Okay, so you see DMD on the bottom, right? So light goes to DMD, then it's folded, okay, a few times, then sent to a dichroic, which transmits the red channel, which covers 2 to 4 microns, and deflects the blue channel that covers 1 to 2 microns. Okay, we are able to cover 1 to 4 microns by splitting that into 2 channels, blue and red. Okay, so this is actually my conclusion slide. So what's the bottom line? We still want to know what dark energy is. Is there dark energy, right? So what's the reason that the acceleration of the universe is speeding up? And to do that, we need definitive measurements, okay? So I walk you through what Euclid and Roman will do, okay? And I argue that we need Atlas beyond that, okay? So there's, I think to solve a fundamental mystery, such as dark energy or cosmic acceleration, we need to have a step-by-step plan. You know, you can't get there in one step or overnight, definitely not, right? So it's a decade-long process in which we need to make more and more progress in order to achieve at some revolutionary insight. Okay, and so here I conveniently worked out the galaxy number density for Euclid, Roman, and Atlas for you. Okay, so for Euclid, we expect the galaxy density around 1300 per square degree. For Roman, that goes up to 5,000. For Atlas, goes up to 72,000. Okay, and so the denser we trace cosmic large-scale structure, the better we can employ higher order statistics like the 3-point correlation function, right? I showed you that really gives you the definitive measurements and also will allow us to model the systematics much, much better. All right, I'll stop talking now. Thank you for your attention.
Okay, questions? Mike.
Hi, Ewan. It's Mike Hudson. A little bit off the topic of the main thread of your talk, but can you remind me, I should know this, but Roman obviously has its high latitude survey, but I forget if there are plans for deep fields. And if yes, do those overlap the Euclid deep fields or are they somewhere else?
Mike, excellent and perfect question. So yes, Roman will absolutely have deep fields. Which ones are actually under review? So there was a call for proposals for pilot surveys on Roman, and there were several proposing various possibilities for the deep field. I think I was even a co-author on one of those. I think there's a strong push for doing 1 square degree extremely deep. Then, of course, for the Roman galaxy redshift survey, I actually put in the science requirement document that we need a calibration field for purity and completeness on the order of around 22 square. And I was also co-author on some report or white paper in which we argued that overlap with Euclid will be highly beneficial. So the constraint there, Mike, is that for the calibration field for the Roman galaxy redshift survey, that calibration deep field needs to be part of the Roman galaxy redshift survey footprint, which may or may not overlap with Euclid.
Thanks.
You're welcome.
Other questions? Let me ask mine. What's the timeline for decisions on Atlas? Has it changed recently or?
Okay, so Atlas, brief history. So I started that in 2015, right? So we responded to call for probe mission concepts. We were actually ranked excellent with no major weakness, but not selected mysteriously. So we carried on, and it's a huge interest in the community. And 2 years ago, I was invited to present Atlas probe to the 2020 Decadal Committee. And in the EM2 electromagnetic observations from space panel 2 that covers the Atlas wavelength range. In the panel, in the report from that panel, Atlas was actually ranked #1 in science, okay? But then you guys may or may not have heard. Unfortunately, the Decadal Committee killed off all probes except for far infrared and X-ray. That's why we're forced to descope Atlas from a probe, which is $1 billion class mission, to a MIDEX, right, which is around 400 million, still a lot, right? So what I've found, thankfully, is that Atlas Explorer can still do most of the science of Atlas probe. For cosmology, the impact is almost negligible, because we don't need to go that deep. And so what's the timeline? So the next NASA MIDEX call is in 2026. So we do plan to submit a proposal. And we do have a team in place that Mike is part of. So we've been doing this for so long already, and I think we have the most compelling. We can't do probe anymore, we're not allowed to, but now we have the most compelling MIDEX Explorer mission concept. So we will carry on and fight for it, and hopefully it will eventually happen. And so we want the community to be aware that there's something like Atlas that everyone can support and help make happen.
Thanks, Yun. James, you have a question?
Yeah, my question was, so given there's a slight delay between Euclid results and Roman results, do you think there's anything Euclid might find about dark energy which, basically reduces your interest in exploring it further? I mean, what happens if Euclid gets some plain vanilla result to within their error bars? Is that a problem?
Good question. I think just the opposite, right? So dark energy is such a fundamental problem. Mm-hmm. We really need to know what is it. So if Euclid gives us measurements that are consistent with numbness with cosmological constant, mm-hmm. That will be so frustrating, disappointing, yet might happen, right? So that I think will put more incentive to Roman allocating more time so that we can, achieve mm-hmm. significantly improved statistics and, much better controlled systematic compared to Euclid, so that we can actually say, well, even down to what Roman can tell, here's what it looks like, right?
Mm-hmm.
Okay.
Okay, thanks.
Any questions? No? Okay, well, let's thank Yun again for an illuminating talk.
Thank you, my pleasure.